Hello everyone. Good morning to all. I welcome all on the 8th day of this AICT sponsored 2-week faculty development program on cutting edge trends in deep learning approaches. I'm also happy to welcome today's resource person, Mr. S. Imayabharati, machine learning engineer, Heuristic Digital Technologies, Chennai. He completed his BE Computer Science and Engineering in Anna University and M.Tech in Data Science and Engineering from BITS Pilani. He specialized in natural language processing. Currently, he is working as a machine learning engineer at Heuristic Digital Technologies, Chennai. I assure that all the participants will get an in-depth knowledge in recurrent neural network and also enjoy this session. Now, I request Mr. S. Imaya Bharati to continue the session.
Okay. Thank you, ma'am, for those kind introduction. As she mentioned, I'm a machine learning engineer by profession, and I'm a NLP engineer by trade. So most of the time, I've worked on natural language processing. All my projects and every product that I developed in my company mostly belongs to natural language processing domain. So, recurrent neural networks, as you all might know, it's a branch or it's a subdomain that emerged from natural language processing as an main domain. So, we would get into recurrent neural networks and we'll see how it works or the intuition behind recurrent neural networks, and we'll also try to get the mathematics behind the recurrent neural networks. So I'm going to share my screen. Also, I would very much like to have an interactive session if possible. Uh, Please feel free to ask any question, any doubts, not only from recurrent neural networks, in any academics related to machine learning as well as AI or deep learning related questions. You can ask anything. We'll have a time for Q&A if possible. You can ask me in any related domains. I'm also a research person. Recently published a paper. I'll let you know about that at the end of this session if time permits. So, in case if you have any research related questions, please feel free to ask. And yeah, so let's get into this session. Okay, so the screen size is okay, and the particular font format is fine by everyone, right? It's clear, correct?
Yeah, it's clear. You continue.
Okay, super. So, as ma'am introduced, it's going to be a session on recurrent neural networks. And as I said earlier, recurrent neural networks is a sub branch of NLP, natural language processing, which again is a sub branch of artificial intelligence, as well as deep learning or machine learning for that matter. So today's lineup is all about understanding the history of neural networks, or where all this AI boom started from. What is the origin of that story? Why it is much relevant now? Why it is not then, but why it is becoming more and more relevant now? As well as we'll go into the traditional things like uh, what are all the types, what are all the applications, what is the advantage and disadvantage, what is the mathematics behind LSTM, that is LSTMs. We are also going to see about LSTMs and GRUs. Recurrent neural networks is like a holder, which cup holder, or it's like a cup which holds two kinds of architecture in it. Recurrent neural networks is a generic word which represents something that mutates or transforms itself during time, or learns itself during time. That is the generic terminal representation of recurrent neural networks. But the original architecture behind recurrent neural networks are from LSTM as well as GRU. That is where the recurrent neural networks evolution stopped, because as we all know, science is all about evolution. From recurrent neural network, people transformed into some other architectures. We'll also see that in this session. So recurrent neural networks will get into the deep understanding of how it performs, what is the mathematics behind LSTM, what is the mathematics behind GRU, all those things. Again, since it's like more than one session for you people on artificial intelligence as well as data science related subject, you might all have been had the notion that data science is nothing but mathematics. It's all about maths behind some fancy terminologies. Whenever I say recurrent neural networks, it's nothing but a linear regression happening in a timely fashion. Whenever I say a neural network, it's nothing but a huge weightage matrix. Imagine yourself that there is a huge matrix lying around, and you are doing a master following from that matrix based on the index and column, that is based on the row index and the column index. That is what a neural network is. And linear regression, evolved linear regression is what recurrent neural network is. But people who coined those terms, people who developed those terms, had a great intuition behind that, so it became so popular. So the initial understanding or the initial knack that we need to have on AI or data science or machine learning for that matter is there is a huge scope for research, there is a huge scope for finding new things, but the intuition behind those should be right, and the intuition behind those should be formed based on the history. So whenever you say that I'm going to develop something new, I'm going to develop a new architecture, you should know the history of that particular architecture that you are carrying forward. Let's say, as I said, there are only two architectures till now for recurrent neural networks. I mean, three. There is a simple architecture. We'll also see that. So there are only three architectures. Let's say you're super impressed by this recurrent neural networks, and you started carrying on with the research on developing a new architecture. The one thing you must know is what is the history behind the recurrent neural networks, as well as how it performs, what is the time complexity, space complexity, all those data structures related term. And the primary thing that you should have in mind is what is the mathematics behind those RNN or LSTM or GRUs, so that I can form a new mathematical equation. It all comes to mathematics in the end. I am a science person. Don't mistake me, like since I'm talking more about mathematics, don't mistake me on I'm a math enthusiast or something like that. I'm a science person, which means I love physics, I love chemistry and those equations and stuff. But when it comes to artificial AI or when it comes to machine learning, mathematics is the core behind it. Everything started from there. So it's very important to know what's the math behind there, what's the ideology of that particular equation of that particular math is lying around, or it has been developed on some ideology, right? What is the ideology that we should know in order to understand machine learning or AI better? So whenever you take a course, whenever you take a YouTube video, or whenever you take any resources that are related to AI, ML, or DL, please keep this in mind that mathematics is everything. Don't plainly try to understand what's in the paper, what's in the course video, or something like that. Please keep in mind, or only view the resources like videos, blogs, anything. View those if they have mathematical explanation for them, because it's all in this particular scenario, it's all mathematics, right? So keep this in mind. Just an timely update, which has to be known by everyone in this field, because people are coming into this field assuming that everything is there available on the internet. I'll try to start this, and I'll try to understand, or I'll try to get into ML. I'll use Python. So it's not the case. The case is this: you have to understand the mathematics behind it, and then you can code it in any language. Even C, C++, any language you can code machine learning. But the problem is people who are coming in newly, they have this assumption, and those advertisements, those courses they are hosting, people are hosting, they say that you don't need a single line of program to create a neural network, something like that. It's not the case. Coding is not the issue here. The main issue is the mathematics behind what is there. So since you are all professors and you will be teaching these stuff to the next generation people, I would very much like you to have this intuition in mind, so that whenever you are explaining things to someone who is going to enter this industry, it would be lovely to see people who understand things well, and then who goes to the mathematics part of AI data science first and then come into the coding part. We should first get into the mathematics part, understand the equation, understand the logic behind it, and then come into the coding part. That's the primary state or primal state that we need to take. Right now, it's like interpretability on machine learning, interpretability on neural networks is evolving very much. As you all might know, it's a huge research field, because people, when data science or AI started, people easily said that I'm going to come into data science, I'm going to use Python. It takes only 4 lines of code to develop a neural network, but that's not the case. You need to understand what neural network is. If you can't simplify something mathematically, then you don't know that thing correctly. That's the whole idea behind why we should learn mathematics before we come into AI or ML. So, uh, so this is the lineup for today. That I mean, agenda for today. We'll go into each and every individual unit one by one, in the chronological order. So first, let's get into history of neural networks. As I mentioned earlier, knowing where it started, knowing where it all began, is very important. Very important in understanding, or very important in finding why something happened, why something came into this picture, why it evolved, or it also helps you in where you should, or where someone should take the course on that particular topic. So history is very much important in each and every case, not only in AIML. History is very much important in all the topics that we study, all the topics that we discuss. So if you don't know the history, please don't carry forward with anything, because you will never reach some place using just the intuition that some people said about something. So let's say you're talking about a perceptron model. If you don't know the history, don't carry forward with any research or something, because it's more likely you will fail with the process that you're trying to do, or with the work that you're trying to do. Because let's say you want to invent something on the perceptron model. You say you and finally you have accomplished the task, but you can't guarantee whether they have someone have already done that, or you can't be sure that whether it's acceptable for this particular model to have this particular logic or intuition behind it, because you don't know the history behind it. So before going into that, I just wanted to apologize for this watermark that you are seeing here, because I tried to find some scripting tool, and the only free scripting tool that I had have this watermark around it. I tried removing it. I tried different options, work around for it, but I was not able to do that. Since it's a I'm not able to do that. So my apologies for that. So again, let's continue to the session. Frank Rosenblatt invents perceptron while working at a Cornell Aeronautical Laboratory. So if you see, the idea behind neural networks, the idea behind AI, the idea behind machine learning, everything came from an aeronautical laboratory. So it doesn't even belong to any kind of computer science. It doesn't even belong to any kind of computer related work. It all started with the aeronautical laboratory, because there they had this problem that they wanted to invent some kind of weightage based matrix that can solve the flight pattern problem. That is where it all started. See, the core of what we call as primal computer science domain, or what we call as the top of the food chain computer science domain, started from an aeronautical laboratory. So this is why you should know your history better. You will never know where a particular problem can be used to solve, where a particular idea, where a particular research can be used to solve a problem until you know the history. So always try to get into history first. So Frank Rosenblatt invents the perceptron model. He said that uh, it all starts when a model is able to correctly predict a flight's pattern based on a weather. So whenever there is some kind of cloud adjustment, whenever there is some kind of air shift adjustment, people will try to the flight persons, that is the pilots, have to adjust their course. So let's say the idea behind the perceptron model is using those two inputs, the shift in the air, the wind shift, as well as the shift in the clouds. They use those two inputs to accurately predict which direction the flight should take in order to avoid some damage for the aeroplane the uh, or the course that it's taking. So these two things has to be aligned together in order for the aeroplane to fly together from one point to next point. Correct. So the Frank Rosenblatt perceptron model initially worked in a way that it takes two input and then predicts the flight course direction that it should take. So that is where it all started, and people started saying that this is the start of human controlling. This is the start of machine controlling a mission. So it generated a great deal of shockwave around all the industries, because it's in 1957. If you see, it's invented in 1957, and that is when they called it as an that is when they coined the term perceptron. Perceptron is nothing but a thing with a brain. So again, people, once there is an hit in something, there is a hit in any kind of research area, people started to use that, right? So all kinds of people had different ideas, different notions for how to use a perceptron model, and they started solving different problems using the perceptron model. But the problem at that time was there was no there was no hardware that can support the perceptron model, hardware that can support the huge matrix, hardware that can support huge computation power. So you might know that the first satellite that is launched contain only 4 MB of RAM, right? Just 4 MB of RAM. Uh, the very first satellite which launched had only 4 MB of RAM in it. That's the maximum amount of RAM that they can give it to a computing power at that time. So they invent a satellite with lakhs and lakhs of rupees. I mean, lakhs and lakhs of dollars, millions of dollars. The maximum amount of computation power that they can give to the satellite is 4 MB of RAM. That is how the limitations are in place at that time. At the time, by at that time, I mean in 1950s, 1960s, those times. So then in 1969, Marvin Minsky and Seymour Papert, they started writing a book called Limitations of Perceptron. I would very much recommend or very much suggest that you start go into that book, get an idea behind it, what is the analogies used in that book, and the core concept of that book is very much important, and it contains the more likely evaluation of what is happening in the AI, what has happened in the neural network as well as AI domain. Okay, so the limitations of perceptron showed that we can't continue research into the neural network domain because of the hardware limitations and because of the time it takes. At that time, that is at the time of 1960s, 1950s, there has been a lot of time taken to review something. Lot of time. There is no connectivity at that time, right? So there has been a lot of time taken to review or at least accept something widely that it can be used for any generic purposes. So because of that, and because of the hardware limitations, they said that this is the stop of perceptrons, and there is no evolution behind it. And in 1982, John Hopfield popularizes Hopfield network. So he created a network which is likely to be called as recurrent neural networks at his time, and then they widely accepted that it is a form of recurrent neural networks. So why John Hopfield network started recurrent neural networks is it had a content addressable memory system. Okay, content addressable memory system meaning consider your RAM as a type of memory. If anyone has seen how RAM looks or the physical identification of a RAM, you will get to know that it has many. I mean, if it is a DDR3 or DDR4 RAM, it will have some uh, 8 cells in it, 8 chips, IC chips in it. So if you see that, those are the content addressable memories that John Hopfield used to store the state of each and every iteration. Let's say there is an recurrent neural network. So I'm sorry. Let's say there is a recurrent neural network, and it has an address attached to it. By address, I mean it has a memory attached to it. So whenever some kind of, let's say you pass a data set of 50 data points, and for each iteration, whatever the weights, whatever the values that comes across each and every neural network, it will store that information in a memory. So that information will be used when a new input comes in order to determine whether this particular information that is stored in the content addressable memory has to be used or not. Okay. uh, so here the state information is addressed by storing those information inside a memory block. Information about each iteration is stored, and then that iteratable memory that is stored in the content addressable block is will have an index which will be used to identify the particular weight matrix or a particular address that we need to restore for any given input. Okay, here the state means information about each iteration. So this is nothing but a system's RAM component. The state is nothing but content addressable memory system is nothing but uh, a RAM component in a system. Okay, so let's get into RNN instances. We have, as I introduced before, 1986 is the birth of recurrent neural network, and in 1997 LSTM came in, and in 2014 GRU came in. So if you take a look at the year gap between 1986 and 1997, it's pretty much like less than 10 or less than 11, around that zone. Okay, but when it comes to, yeah, someone else is presenting, I think. Who's Imran? Uh, are you guys able to see my screen? Because I'm seeing someone else's screen.
Yes, sir, it's not visible.
It's not visible, right? Mr. Imran Alam, can you please stop sharing your screen? Thank you. I'll try to reshare my screen. So now my screen is visible, right? Okay. I think now my screen is visible, so I'm going to continue. In 19, so as I was saying earlier, in 1986 RNN started, and in 1997 LSTM started. So again, the intuition behind why LSTM came in is very important. We'll see about that. But if you see the time gap between LSTM and GRU, it's like more than 15 years of gap, because LSTM fulfilled all LSTM fulfilled all the needs of a time series as well as all the needs of a time related recurrent related problems. That is why there is no development. And another important factor is again the hardware capability. LSTM took most of the hardwares that needed. It is a very high intensive hardware as well as software capacited neural network. So if you use that, it's more likely that you don't have the resources that is available under your any machine under your particular computer to be allocated to anything else. If a LSTM model is training on your machine, then it will be like at that time, I'm saying at 1990s or 2010, still 2010, LSTMs, if they run in your system, then you will never be able to run anything again. That is any applications that is in your system will never get a resource allocated from the CPU or the computing memory to do its process. Even the desktop will fade away because of LSTM running in the background. So due to that limitation, there was no research that can be carried forward. And then came in GRU, which actually uh, minimize the hardware as well as software capacities that are needed to train an RNN network. So RNN is a generic term which holds LSTM and GRU, and then SRNN. SRNN is nothing but simple RNN. So that is like, so you guys are familiar with artificial neural networks, right? I assume that a artificial neural network session has been taken before this session. So in artificial neural networks, there is a term called vanilla neural networks. Correct? Vanilla is nothing but it's a plain neural network. Like that, here we have SRNN, which is similar to vanilla RNN, which has a plain recurrent time step, and RNN cell. And then came in LSTM, and then came in GRU. So these two are the primary architecture or the essential architectures of RNN. Till now, there is no development across RNN architecture. If anyone is interested in doing so, please feel free to do, because it's a wide research area. So yeah, so these are all the instances, or these are all the types of RNN models, and this is the timeline. RNN applications. RNN applications, they have huge variety of applications people are using. So whenever you are learning something in AI, machine learning, or DL, please keep this in mind. There is no limitation in where to apply this particular logic or where to apply this particular model or something like that. Okay, because if you understand it clearly, then you will be able to apply that particular problem anywhere. So when you learn linear regression, it is not necessary to use linear regression only for a numerical data. You can also use linear regression for image captioning or for image classification. It's the way that you represent the information to the model is what matters. Okay, the contextual representation. How do you represent a particular form of data without getting rid of the contextual meaning behind the data is what important in any kind of machine learning or AI or ML model, AI or DL models. So in RNN applications, these are some of the applications that RNN hosts itself. There are huge variety of applications in it. Please go and look into those. You will get a great deal of information from there. Image captioning is nothing but let's say there is a video frame or an image which has a bridge, a person, and a dog the person is holding. So how RNN works is in image captioning. How RNN works in image captioning is it will try to accumulate all the aspects of that image into a particular caption. Okay, so how it does is, it will for the particular image that I have said now, it will give an captioning like person holding a dog standing near a bridge. That is a particular caption it will give. It's not classification, it's captioning. Each and every element in the image will be identified and it will be phrased as a sentence. So RNN is basically a sequence to sequence neural network, model. So when I say sequence to sequence, whenever there is a particular bit of information available for any kind of data, that is called as a sequence. And then if the same bit is changing over time, that is called a sequence to sequence data. So RNN can be used across any sequence to sequence data. Okay, and machine translation. Machine translation is nothing but converting or translating one language, text from one language into another. Okay, so let's say you have a textbook in English and you want to convert that book into French. You can train the RNN model to do the conversion. So as I said, applications is not limited to any concepts in AIML, correct? The best example for that would be Google recently announced a new feature called you can scan an image, Google Lens, I guess. You can scan an image in any place. It will provide where it is. So it will provide from the image, it will gather all the information that it needs, and it will provide you with the information that where that particular image has been taken from, what are all the objects that are present in the image, if there is a if there is a board of a particular company, or if there is a digital caption for any particular thing, it will identify that and it will say this particular digital signboard is in this particular location. It will give all those information. What they have done is they have created an architecture which involves two components. One is a convolutional model to identify all the images and stuff, and then the recurrent neural networks model to understand or to identify the text from that image. Okay, so applications is limitless here. You can even try those, like you can go through different architectures and combine that with RNN. You can form a sequence to sequence problem from anything. That is what I mean by applications are limitless. So initially, when you look at the problem that I said for the Google Lens, it's a problem where you need to classify or caption a particular image, correct? But it's not a sequence to sequence problem, because they are going to upload an image and you are supposed to gather the information about that image from just a plain pixel sized image, correct? Then how do you transform that into the sequence to sequence problem is what you should do, is what you will be able to do if you have the right intuition behind every concept. Okay, so the machine translation, they used machine translation, they used RNN, and they used image object detection. These three things have been aligned together to form an product which said that whenever you capture an image, I'll be able to give you all the information that you need from that image. So look how cool it is. Okay, and again, time series prediction. RNN is used in time series prediction from the start. Whenever at the time it started, it was invented or it was coined, the RNN has been used to use in time series prediction. So time series is essentially a sequence to sequence problem which varies across time, and RNN is particularly suited for this problem because it will be able to hold the information for very long. So why time series prediction is important? RNN is important in time series is any other data, any other model that you try in AIML apart from reinforcement learning will not be suitable for this time series prediction, because uh, time is an time is not a constant variable. Whatever happens in time, you cannot predict that perfectly until you know what happened when a series of factors accounts for a particular thing that happened over a time. Let's say, let's say someone is driving a bike, and the particular factors are the braking capacity of that bike, the acceleration speed that the particular person is driving at any instance, and then the mood of the person. These are the three factors that might involve in what is going to happen in the next few seconds or the next 5 minutes. So what are all the possible things that can happen? Either the person can increase the throttle, either the person can apply a sudden brake, either the person in a bad mood decides himself to do a rash driving or something like that. These are the three things that can happen. Correct? So if this is not constant across time, correct? This is not going to be constant. But how we can use RNN time series data is, let's say an event like the person is having a braking capacity that is not working properly. Let's consider this event as happened already. Okay, so the person riding a bike, and that bike is not having the proper braking capacity, and he has he has started throttling the bike very fast, and he is not in a good mood, and then he crashed his bike into a, a vehicle driving opposite to him, or a vehicle driving parallel to him. This has happened already. So for any neural network, for any machine learning or deep learning models, if you train a model with a particular information, like let's say this is one instance, and there are like this, there are many other instances where the person has not done something like this. So when you use a neural network or any particular deep learning model, it will try to associate any new data point. The data point contains three things: the braking capacity, the throttle speed, and the mood of the person. It will consider these three things, and it will try to predict whether he will crash or not. Correct? But the problem here is, it will never know what is the influence of each and every particular thing over what is going to happen in the next time step. Yes, but in RNN, it holds this particular information across each and every iteration. So whenever I input which is has a similar resemblance of an event that has happened before, it will be accurately able to get that outcome of that particular event which has a huge resemblance with the current event. It will be able to get that particular output, and then it will try to predict that now an accident is going to happen from this time step to the next 15 time step. So there again, this is yet another application of this is yet another ideology or analogy for there is no limitation in applications of any machine learning or deep learning models. So again, this will be a huge step in saying that these are the kind of things that causes accidents in a driveway. Correct? So this is why RNN is widely used in time series prediction. It will be able to it is able to store particular information across time. And handwritten digit recognition is nothing but there is a CNN model for very first time when an handwritten model came in. It is for convolution. It is for convolutional neural. It is from convolutional neural networks. Okay. But what happened with that convolutional neural network model where it failed is it is not able to generalize across different handwritten patterns. But RNN is able to generalize across different patterns, and it has been widely accepted for handwritten digit recognition. Okay, these are all the applications of RNN given uh, given some of the proper concepts that have been implemented over RNN architectures. Now we are going to see boon of RNN. Boon is nothing but advantages or the pros of RN using an RNN. So let's say you have a data that has three data points as an input. That is, you have a data with three columns, and then you are trying to predict an output. For linear regression, the output can be like for a regression problem, the output can be like anything with the floating or decimal point number, correct? Because it's a continuous data. For classification, it's going to be from any classes. It's going to be from any classes like 0 or 1 or 0, 1, 2, 3, 4. How many classes you want. But the data that you have or the data that you face, let's say that you have three inputs and you expect the model to produce 6 or 7 different outputs given at any time, and you also expect the model to work given 2 inputs and mimicking or minimizing one input from the data point. Okay, so if that happens, you want the model still to work. Will that be possible? In any machine learning, deep learning methods, this is not possible. When you train a model on a particular dimension, what I mean is the rows and columns of your data. That is what I mean by dimension. Let's say you have 1,000 data points and you have 3 columns. Then the model expects each and every input in the test data to be in this particular format. That is, each row should contain 3 values. It will never compromise for any other things. Okay, so that is the case here. But let's say you want to have so the classic example of this variable size input is you are trying to convert from English to French. Okay, so you say get me a cheese. That is the English sentence that you're trying to say. And for French, it's like get me a cheese. It will be transformed into royal with cheese. See, there is a complete transformation between the size of the input to the size of the output. Both the size of input and the size of output has been changed. You will never get this feature in any kind of machine learning, deep learning, or AI models except RNN. It has the very prestigious advantage over all the deep learning or machine learning methods that it can account for variable size input. You can provide input of any size to this model. And the second most important thing is it remembers. Consider you're able to generate an RNN model with a huge memory dedicated to a particular model. Okay, the best example or the most interesting example would be, let's say you are trying to predict the price of the stock market, predict the price of a stock in a particular stock market. Okay, so for example, let's say it's BSE, that is Bombay Stock Exchange, and then Bombay Stock Exchange, I think it started in 1967, if I remember it correctly, around 1950s. I don't remember. I'm not sure. So let's say it started, for the argument's sake, let's say it started 1950, and from 1950 to 2020, there will be a collection of data for a particular stock, and let's assume that stock is Tata Motors. Okay. So if you have that much amount of data, every pattern that is possible that has happened across history will be laying down in that pattern for you to find, for the model to find. Okay. For that to happen, you need to train a model which has a sole dedicated purpose to learn from this particular strain of data, and then whenever a new set of input comes in, It will try to predict what will happen, whether the price will go up or down, or whether the what is the price at any particular given moment for Tata Motors based on the history. That is what we are going to do. You take any kind of linear regression. So essentially, this is a regression problem, right? You have some input and you are trying to predict a continuous form of output. Correct? It's a regression problem. But regression again, as I said in the machine translation, or as I said in the handwritten recognition, it will try to associate each and every data point into the particular pattern it has already seen. It knows. That is what any regression model will do. But RNN is slightly different than that, because it also holds what happened when a particular outcome is been there in time. What has happened in a particular outcome is been there in time. So when you have a huge collection of data for one particular stock and you want to train a model, RNN is your best bet, and it will actually remember each and every pattern that has happened across history, and you can guarantee that I can guarantee that the model will never fail. What is going to happen? The model will never fail in predicting the stock price of the Tata Motors after training, because you have shown the model what are all the possible cases. There is no if else. What is going to happen if and what is going to happen else. There is no if else in this case. You have shown the model what are all the possible cases that can happen across time. It's almost like 50, 60, it's almost like 70 years worth of data. And you have shown to the model this is what happened over 70 years. Right. So keep in mind, this is what going to happen in the next input when the next input comes in. You can be so sure that if you train a data with that dimension or that big, you will be sure that at least for the next 30 years, your model will never fail in predicting the stock price of Tata Motors. And finally, it has a memory. What do I mean by it has a memory is, it can store information. This is one of the main or most important concept of recurrent neural networks. It can store information which can be retrieved again. This is mostly in resemblance with what our human brain does. We are storing terabytes, petabytes of data in our human brain, and whenever needed, we are collecting it. That is the basic or most primal intuition behind RNN. So we are storing the information. Whenever we need it, we are resurfacing that particular information in order to do our work perfectly. Okay. So these are all the pros of RNN or advantages of RNN, and mostly I use those fancy terms because it looks nice in a presentation. So these are all the boons of RNN. Okay, and let's go to the cons or disadvantage or bane. Gradient vanishing, exploding gradients, memory requirement, computational complexity. These are all the disadvantages of RNN. Okay, so let's say you have a you have seen artificial neural networks, or you have seen linear regression and stuff like that, right? I assume previous sessions have been on that. So you know what is gradient, and you know the gradient method of attaining the best optimal activation function for a neural network, or the optimal line for uh, the linear regression or the things, right? So anyway, I'll give an example also. So what happens in any neural network or any any linear regression model is you will try to form a line or fit a line function that is gonna represent your data very well. Given the x, what is gonna be the y? This is what you are gonna do in your linear regression, correct? This is what you will do in your linear regression. So initially, what happens is, one second. So initially, what happens is it will form with a random line. It will form a random line, okay, and there will be a center point to it, center point associated with it. That is the m slope function. So what we will try to do is we'll try to have a gradient graph. What is the gradient graph is we'll decrease the slope, that is m, for this line function, so that the error term is decreasing. This is what we will do. This is our optimal point, that is the optimal slope value for the given data on this line function. So the line function is this: y equal to mx plus c. I'm sure you have been bored by this equation, because any machine learning or any data science lecture, they will start with this y equal to mx plus c. So essentially what we are trying to do is, well, we are trying to reduce or get an optimal slope function that might represent the dependent variable, that is the input variables that we have, which is x, and the output variables, that is output variable that we are trying to predict, that is y, and this is our constant. Okay, so we are trying to alter this particular line function in order to reduce the error term. Error term is nothing but your x is this and your y is supposed to be this, but the current line function is predicting this. Then what we will do is we'll try to change the line. Then the line will be drawn like this. Sorry, then the line will be drawn like this. The line will be drawn like this. So again, the center point hasn't changed, but if your x is this, here you will be able to predict your y. This is the lowest term possible, lowest error term that is possible. Then we are going to say that lowest error term is my wherever I get a lowest error term for a particular slope value m, I will fix that. That is going to be my optimal slope value. Yes. So given this particular analogy, what gradient vanishing is, since we have a memory in RNN, if we try to reduce the gradients each and every time step, what is the most probable thing that going to occur is, there is a case where the gradients is going to vanish. That is, it's going to go in the minus value, but it shouldn't happen, because every case in mathematics has an optimality, correct? So if you say this is the lowest, it shouldn't be possible to go to more lower. From that lowest point, it should go higher. That is the optimality condition. So whenever for this particular gradient vanishing problem, if it starts going in the minus direction, that is the negative direction, there is no limit for that. It can start from -1 and it can go to minus infinity, correct? There is no limit. That is the problem behind gradient vanishing. You will never know where the gradient is going to go. That should not happen here. That is one problem with the RNN. And then exploding gradients. Exploding gradients is nothing but you are trying to find the optimal point and you are storing the information in your content addressable memory. The most probable thing that can occur while doing this particular operation is you can start from a very huge gradient and try to go to the very optimal point, but it might take so much time for this particular thing to happen, because gradients are, as I said, every neural network, every machine learning problem starts from a random state. Every equation starts from a random state. And then it will try to learn. By learn what I mean? By learn what I mean is it will try to update itself with the new information that it has been presented with. It will try to update itself with this new information. So when that is happening, if you start if the random state starts at a very high pace, very high place, then it will take so much time for the neural network or the recurrent neural network to attain its optimal point that the model will fail. So it will assume that this is my lowest. So far I have come this line and this is my lowest, and it will say enough, I'm not going to do any more training, this is my lowest. So again we have a exploding gradient. So what is memory requirements? Memory requirements is nothing but for an RNN initial stages. These are all the initial conditions of RNN, and then came in the LSTM which solved these two problems, exploding gradient and vanishing gradient problem, and then came in GRU which solved these two problems, memory requirements and computational complexity. That has been solved by GRU. What is memory requirements? Memory requirements is nothing like it's nothing but having a huge hardware based machine in order to train a simple RNN. Initially when it started, you need to have more than 30 or 40 GBs of RAM, 32 or 64 GBs of RAM to train an RNN model for a simple task. That's how the memory requirement was, because you have been storing information for each iteration. Let's say you have 1000 data points, okay, and for each data point you are going to compute a weight matrix, and that weight matrix is going to be let's say size of size 1 GB, of size 1 GB, okay. Then if a model trains for 10 iteration, and for each iteration it goes across 10,000 data points, 1000 data points, 1000 data points, and for each of this operation you are going to get a 1 GB matrix. So if you wonder whether a 1 GB matrix is possible, it is possible, because when you go into proper research side of neural networks or research side of any application for that, any AI based application for that matter, the matrix size is limitless. I have been dealing with a matrix which has 12 GB of size. I've been dealing with a matrix that has 12 GB of size, and I'll do computations, I'll do slicing and dicing on that particular matrix, and then I'll produce results from it. And I have, for my model to run, it needs 6 of this 12 GB matrix. Okay, that essentially means that I'm using 72. I'm using 720 GBs or around 100 GBs of around 100 GBs of data for a particular computation. So if you take this particular example, 10 iterations, 1000 data points. For each data point, I'm going to store 1 GB of data. Then it's going to be like 10,000 GBs of data when the initial in the initial stages of RNN development. So you need huge computation. Okay, so that 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 is the memory requirement problem, and then comes in the computation problem. In order to process this 10,000 GBs of data, you need that much of computation power. That is also very vital in this case. So it is also like it is also an essential problem with an RNN, and it has been dealt with. These two has been dealt with in the GRU, in the developments of GRU. Okay, I think it's 11:05 now. We'll take a 10 minutes break. We'll reconvene at 11:15. Okay. Okay. Hi, people. Shall we continue or let's wait for 1 moment or something? Huh? Okay. I think I will continue the session. Uh, I'm sharing my screen now. So just to give a quick recap on what we have seen so far is we have seen about the history of neural networks. We have seen the types of RNN or RNN instances, as I would like to call it, and then we have seen RNN applications. We have seen the advantages and disadvantages of RNN, that is recurrent neural networks. Let's get going. So it all started with a single simple recurrent neural network cell, which is for which the architecture is this. For which the architecture is this. It has a input unit. It has a recurrent input. It has a sigmoid function, gate activation function, which is always a sigmoid function, and then it has an output. It has a recurrent. What is this recurrent is? Uh, it's nothing but the information of this particular iteration, this particular state, will be given as a recurrent output. This output will be fed to the cell again. So how this particular recurrent neural network transforms is or unfolds is like this. So this is a cell, and then this cell's information will be passed on to the next cell. It will have an input unit. It will also have an input unit. So both the input and the recurrent information will be passed on from cell to cell in this particular RNN architecture. So whenever I say RNN architecture, LSTM architecture, GRU architecture, it comprises of a sequentially connected RNN cells or LSTM cells or the GRU cells. The architecture is nothing but sequentially connected RNN neural networks. That's it. The way the information is passed, represented, and carried forward in a particular cell is what different from a SRN or an LSTM or a GRU. That is what will differentiate each and every RNN architecture. Okay, so we have seen what is simple recurrent network. We'll see what is long short-term memory block. This is just an abstract view of what is. This is going to be an abstract about what is LSTM, how the LSTM block looks like. We'll go deeper into this in the following slides. Okay. So as I said, we will have an input. Every RNN architecture, every RNN cell, any kind of RNN cell, I mean the LSTM or the GRU or SRN, will have a recurrent as well as input. These two are non-negotiable for any cell, RNN cell. Okay, and then it will go to a forget gate. What this forget gate means is whether the state information should be allowed for the computation for this particular input, or we can forget it. That is what will happen here. Forget meaning we will never use this particular information, but it will still be stored in the architecture. That is, it will still be stored in the content addressable memory systems. Okay. So input comes in, and then for that input, we will calculate the block input, and then for the particular input, we will calculate the cell state, and then using an output activation function, we will try to produce an output, and then we will try to produce a recurrent output. These three things will be happening in any LSTM block. Okay. Let's see how it performs and the types of RNN. One-to-one is used in time series because we have a single variable, that is our output variable, which is going to be the stock price or anything, and then we have one-to-many, which is used in which is used in image captioning, and then many-to-one, which is used in sentiment classification, and then many-to-many, which is used in video classification. If you take a look at it, for image captioning, for image captioning, what we are essentially doing is we are taking an image and then trying to find different. We are taking an image and then we are trying to split that image into different aspects and then try to classify the different aspects or caption the different aspects, which will form a sequence of words or sequence of strings. Okay, that is what happening in one-to-many. When it comes to many-to-one, when it comes to many-to-many, mission translation as well as video classification, what happens here is a video comprises of multiple frames of image. Multiple frames of image stacked together will form an video. What we are trying to do is we will essentially cut down that video into each and every individual frame, and then we'll try to find different aspects, or we'll try to get a feature out of this particular frames, and then we'll try to classify that particular video frame into whatever data type that we want, whatever data output that we want. That is what the difference between one-to-many image as a captioning and many-to-many image as in video classification. Sentiment classification is nothing but we will use multiple data points to predict whether a particular output is 0 or 1, or whether it's going to be positive, negative, and neutral, or whether it's going to be angry, sad, uh, good, feeling good, very good, or something like that. Those sentiments you can define as the by you. I mean, what is defined in the data set is what we use as a sentiment here. But essentially, it's going to be one single output. There would be no multiple forms of output. So here there will be multiple outputs which will be combined together as a final output. Here there are multiple outputs again which will be combined together as a single output. For one to one and many to one, will have only one single output which is coming out of the system. Okay. So these are all the types of time series or recurrent neural networks. The mathematics behind RNN. I will try to keep this as informative as well as interesting as possible. But since it's mathematics, it's going to be still it's going to be boring. Try to keep up with me, or you can ask me questions at any point. You can ask me about anything on this particular event, on this particular mathematics equations. So before getting into mathematics behind RNN as well as mathematics behind LSTM or CRU, I would like to first say what is a weight. What is a weight? And whenever I say a weight function, a weight matrix, or anything related to weight, what it means. Okay. So weight represents the strength of connection between units. As we have seen earlier, each and every recurrent neural network architecture will have its own cell, which we can also call as units or cells. So the connection between these two cells, the connection that should be established between these two cells is represented in the weight. If the weight from node 1, that is cell 1, or block 1, LSTM block 1, LSTM cell 1, you can call it in any annotation or in any representation you want. But if the weight from one cell to another cell has a greater magnitude, it means that neuron 1 has greater influence over neuron 2. Weight brings down the importance of input value. That is, it plays a major role in deciding what are all the input data points or what are all the input features that we should consider for providing an output. The weights near 0 means changing this input will not change the output. Negative weights means increasing this input will decrease the output. Weights also decide how much influence does a particular input is going to have in the output prediction. Okay, so I have explained about weights, but before getting into the weights, before getting into this mathematics, I'll just visually represent how it is and what it is. Let's say you have a fully connected neural network. Okay. I'm really sorry for this drawing format. So I'm using my laptop and my mouse, but I'm not able to bring my A game on this depiction. So assume it's a fully connected neural network. I know it doesn't look like one, but assume it's a fully connected neural network. This is the input layer. This is the activation layer. and this is the output layer, or we can also call this as a hidden layer. So these inputs will be passed through this input layer, and then it will reach the hidden layers. Here, what important as a weight has here in this architecture is each and every neuron will hold a weight matrix, will hold a weight variable. Each and every neuron will have a weight variable, weight function, whatever we can call. It has a weight. That's the most important point. It has a weight. So each and every weight will decide whether the particular information from this neuron combined with this neuron should be carried forward for the output prediction. How much influence does this input will have over the output that is predicted will also be based on the weight. Again, whether a particular neuron should be activated if a particular input is coming in. Let's say this neuron doesn't need to be activated. This neuron's output is not even needed. Then the weight function is useful in deciding which neuron to activate. If you understand clearly, this actually reduces the computation complexity by 2 folds in any neural network architecture. That is why weights have been invented, or weights, the idea of weighting the matrix came into picture. Okay, because using weights, you can decide whether this particular neuron is activated, should be activated or not, whether this particular input information should be sent through or not. If this neuron is not activated, the computation power that is needed for this neuron to process will not be used. Yes, if it is not used, then the computation power is idle at that time. Yes, correct. So all these information will be holded or stored as a weight matrix. Okay, so that is the importance of weight in any neural network architecture. Okay, so let's get into the mathematics behind RNN. RNN has the following function which represents its each and every cell. Okay, so the function is like this. There will be a weight parameter, and there will be the old state, and there will be the input vector at some time step, or let's say at any time step. How we will calculate the new state? So what we are trying to do is, essentially, we are trying to say, this is going to be my recurrent neural network. One second. This is going to be my recurrent neural network R1. Okay. For this recurrent cell, whether the information about this particular cell to be carried forward, what is going to be the hidden state of this particular cell, and let's say this is our input, this is our old state, this is our R1 recurrent cell, this is going to be our output. Okay, this is going to be our output. So for this to happen, we need to find the hidden state. That hidden state is nothing but having a tan h function of the weight matrix of this particular state information and the weight matrix of the previous state information, or the input state information, along with the hidden state of the previous time step. All this will be calculated and then given as a hidden state, current hidden state. This current hidden state will be multiplied with the weight matrix of the output variable, and then we'll get the output for this particular time step. Okay. Let me give an visualization for what is tan h, what is sigmoid, and what is ReLU. So these are all the these are all the kinds of activation function. Okay, the tan h function is nothing but it can have a value between -1 to +1. That is tan h. Again, we'll have sigmoid, which can have 0 to 1. Okay. Now we'll have ReLU, rectified linear unit, which can have -1 in the x direction and 0 and 1. I mean -1 in the y direction, 0 and 1. So difference between tan h and ReLU is tan h will accept -1 in the y direction. ReLU will accept -1 in the x direction. So it is a slightly relaxed approach in finding the particular component for any given input, or whether to apply or not apply a particular component for any given input. So these are all the different kinds of values that a activation function can take, and this is tan h, this is sigmoid. Sigmoid will only take 0 and 1. If you pass a value to a sigmoid function, if you pass any kind of input to a sigmoid function, it will only say whether it's a 0 or a 1. So it's most probably like a classification final step. Most probably like a classification function. So whenever you want something like some output of any neural network or any layer to be between 0 and 1, you will go for a sigmoid network. If you want some kind of probability, by probability what I mean is, let's say you have different states and you want the probability of this particular state to be known from the prediction, then you can use tan h, because it will give the probability between -1 to 1, and you are okay with having a probability, but you don't want the probability being too liberal. That is, you don't want -1. You want it either 0 or 1 or -1 in the y direction. Then you will go for, if it is in the direction you don't want it, in the y direction, if you don't want -1, then you go for ReLU, which will give -1 in the x direction, which is slightly different from tan h. Okay, that is what happening here. So the next one is the weight matrix. As I said earlier, weight represents the strength of connection between units, and it also has an influence that a particular input is going to have any importance on the output prediction. So how this weight matrix is shared across different RNN cell is this. There will be a hidden state. There will be a hidden state for which there will be a weight matrix, and then for which there will be a input matrix. These three combined together, having mathematical manipulations, will form the next hidden state for this particular time step. This is our time step x1. Okay, this is our time step x1. So for this particular time step, we'll use these three factors to calculate h of 1, which is our next hidden state. Which is our next hidden state. This next hidden state will be used for the input from the next time step. or the second time step. But one thing that is common across all the time steps is the weight matrix. The weight matrix will be initialized randomly at first. I'm sorry. The weight matrix will be initialized randomly at first, and then it will be updated on each and every iteration on the data points. Based on that updation, will form a new will form a new weight matrix that will particularly represent the data points that we trained on. Each and every neural network has its own weight matrix, which will uniquely represent the data problem that we are trying to solve. Okay. So weight matrix is what makes the neural network perform its task on a higher level of abstraction. Okay. So the weight matrix is shared, which is clear now, and the weight matrix will be updated on the training. It will never be updated on the testing. That is, whenever you train a model and you say this is my model, it's going to be fixed, and then after that the weight matrix will never be updated. For any new given input, it will use the same weight matrix to predict the output. So uh, so if you guys have been if you guys are familiarized with the concept transfer learning, it actually involves updating the weight matrix with a new set of input. That is what transfer learning is. So I think you will be learning transfer learning in the next few sessions, I guess. So try to associate this particular concept there so that you will understand, or you'll get a more clear idea on what is happening and how it is happening. Just think about this particular weight matrix example there. So as I said, for training, the weight matrix will be initially randomly initialized first, and then based on each and every iteration, we will uh, we will update the weight matrix, and then we'll form a final weight matrix, which is going to represent uniquely the data problem that we are trying to solve. So whenever a new input comes in, the weight matrix will be used to find, or the weight matrix has an influence over the output that is predicted for this new input. If you want, the concept of transfer learning came in because of this weight matrix, because we will be able to update this weight matrix for a new set of input. We'll train the model again, keeping the original weight matrix. Instead of initializing it randomly, we will keep the original weight matrix and we will try to update this weight matrix based on the new set of inputs that we train on. That is what transfer learning is. So here comes the prodigal son, the LSTM. LSTM cell has the following architecture and the component. The architecture has been shown in the below the right and bottom corner image is the architecture of the LSTM, and the direction it takes is represented in the arrow. It has these components. It has a forget gate. It has a candidate layer. It has an input gate. It has an output gate. It also has a hidden state and a memory state. Okay, so it accepts three kind of vectors. It accepts three kind of uh, activation functions. It also has a neural network. So what are the three kind of vectors is hidden state, memory state, input vector. These are the three vectors. It has three kind of activation functions which are represented as gates. We can call them it has input gate, which is going to be a sigmoid function. It has an output gate which is going to be a sigmoid function. It has a tan h gate, which is going to be a candidate layer, and it also has a forget gate, which is going to be a neural network with sigmoid layer. Here, what I mean by a neural network with sigmoid layer is it will be a neural network, the output of which is going to be either 0 or 1. So whenever there is a say that NN with sigmoid, then we can expect either 0 or 1 from that particular neural network. If it is a tanh based neural network, then we can expect -1 to 1, values between -1 to 1 from that particular neural network. That is what we can expect. So that is why we represent a neural network with a sigmoid layer or a tanh layer, because we know what values to expect from this particular neural network. Okay, let's see the vectors and their intuition. Every LSTM network takes in 3 inputs at any given time. One is the input vector, the other one is the hidden state vector, the other one is the memory state vector, or we call it a candidate layer vector. Okay, so how do we represent a input vector? Is in plain sight, we will just encode each and every word, each and every letter in the input with ones and zeros. For example, the input vector for hello will be this. So wherever, so the length of this string hello is going to be 5. Yes. For this 5-step input, we will have a template vector which is going to have 5 data points. Okay, I'm sorry, 5 data points. So the template vector is like this. It will have first 0, it will have first 0, second 0, third 0, fourth 0, fifth 0. So this is called as a template vector. You initialize a vector with which represents the length of this particular input string that we are taking, and then you initialize the vector with all zeros in it. Then what we are trying to form is, for each and every character, we'll try to form its own vector. Okay, so let's say it's a H, then we know that for this particular input string, the H is coming in the first place. So we are putting 1 over here in the first place. And then we put all zeros. So now this vector will uniquely represent H for this particular neural network. So like that, we'll form vectors for each and every word, or we can form a vector for each and every letters in the data that we have. Based on the problem that we are going to solve, we can decide between whether we want the letter to be a vector or whether we want the word to be a vector. Okay. So the next thing is hidden state vector. Hidden state vector will have all zeros in it, which is then multiplied with a hidden state weight, and then a bias is added to it. But initially, what happens in the hidden state vector is it will be randomly initialized. First, we'll form a template vector as we formed there. Instead of filling it with at the initial stage, it will have a template vector which has all the zeros. Instead of having it completely 0, we'll randomly initialize it from the start, and then we'll calculate hidden state weight, and then the hidden state bias is added. So what is a bias? Bias is a variable that you would consider what is the error term that can happen when you are doing something like this. Okay, whatever process you take, there will be a bias added to it. You will never know where you will make a mistake or where the error is going to happen, what kind of computation error you have done, mathematical error you have done, you will never know. So it's always safe to include a bias which will account for that error, which will take care of the error. If the error state or if the error rate is very high, it will also take care of that particular error. Okay. So the hidden state at any time step will be obtained by using addition from the input weight and the input bias, and then we'll take it through the activation function, which is a sigmoid function, which will decide whether we should carry forward with this hidden state or not. Okay. For example, let's see what is the hidden state vector for the input h will be. We all know the input vector for input h will be this, yes, and there will be a weight matrix and there will be a bias. So what we are doing is, as we said here, there will be a hidden state weight, which is this. There will be a vector from the input, which is this, and there will be a bias, which is this, we are multiplying these two, adding with this, and then what we are doing is we are trying to have an input based hidden state vector. For this input, what is the hidden state? For this input, what is the initial value? For this input, what is going to be the hidden state bias? And then we are compiling all this together into a function which is a sigmoid function, which will return either 0 or 1. Okay, so that is our hidden state vector. So the third vector or the final vector that we have is the memory state vector. Memory state vector is nothing but what is the previous hidden state value if we are going to carry forward the previous hidden state value, and then if we are, what is the input vector that we have and what is the bias that we are going to add, and then we'll calculate the tan h function, which is going to be -1 to +1. So why we are calculating the tan h function here is, why we are using the tan h function here is, we will always carry forward the memory information. Yes, because RNN is supposed to remember, correct? It's supposed to store everything in its memory. So what we are essentially trying to do is, we'll try to hold this memory. If this memory is not wanted in this particular time step, then we will multiply it with -1. So which will have a negative weightage, so the memory will have no impact. If the weightage, if this particular input needs this memory state, then what we will do is we'll receive a tan h function of 1. Then the particular memory state information will be added with the input vector. That will actually increase the input vector's weightage. That is why we are using tan h function here instead of 0 and 1. If we use 0, okay, if we multiply it with 0, it will be lost. The memory information which has been kept from previous state will be lost. We don't want that, right? That is what is essentially happening in linear regression or neural network or any kind of linear models that are possible, that are available. We don't want that. What we want is, we want this memory to be retained, but we want a selection criteria over that memory, which represents whether we should use this memory for this particular input state or not. That selection criteria is what this memory state vector will have. Okay, and the final output is computed using this. We'll have a hidden state, we'll have an output weight, and we'll have this output bias. We'll multiply the hidden state with output weight and then add some bias to it to reduce the error term, and then we'll produce an output vector, which is going to be represented as OT. This is how an LSTM performs in general, or an RNN networks perform, or any architecture is different from GRU will perform. So let's get into a basic intuition. I am a visual person, so my understanding is that if something is clearly depicted for each and everyone, where they can actually see what is happening, then they will never forget it. Then they will have the clear ideology behind what is happening. So I try to get this particular LSTM architecture into a animated animated information. So in case if you haven't understood what I said earlier, please follow this through. You will get a clear idea on what is happening with the LSTM model. Okay. So we have three inputs, correct? We have a candidate layer, that is previous cell state. We have a hidden layer, that is the previous hidden state information. We have an input information, input vector, correct? So first, what we are trying to do, we are trying to decide for this particular input whether we need the hidden state or not. Okay, whether we need the hidden state or not for this particular input is what we are trying to do. So the red color is a sigmoid function, the blue color is a tanh function. So essentially, if it is a sigmoid function, we will receive only 0 or 1. If it is 0, we'll forget that information. If it is 1, we will carry forward that information. For tanh function, we'll get -1 to 1. If it is -1, the impact of that particular information over the vector will be uh, will not be there. If it is +1, the impact will be completely overridden. Okay, let's see how it works. So we have ht, and we have ht -1, and we have x1. Is it clear to you guys, or should I zoom in? Should I zoom in? Okay, I am assuming everyone is able to look into this clearly. Okay, thank you for the reply. So we have ht, and we have ht -1, and we have xt is the input at the current time step, and we have xt here, and we have ht -1 here. Okay, so these two information will be passed to a sigmoid layer, so which will decide for this particular input whether we need the hidden state information or the candidate layer information or not. Okay, let's get into the next state. So we have calculated f of t, which is going to be the forget get output. Let's keep it there. The next thing that we are going to do is we are again going to calculate, pass this through a sigmoid function, which is going to be the input get output, and we will pass this through a tanh function, which is going to be the candidate for this particular tanh function. C t-1 is the previous cell state. We also have f of t, which is going to be forget get output. We are now trying to compute the input get output as well as the candidate get output. Okay, as well as the candidate output. Okay, so here what is happening is, whether this input will need a candidate output is what we are calculating here, right? In the next state, essentially what we are trying to do is we are trying to find whether we need the previous cell state or not. We have the forget gate output. Yes, if this forget gate output is 0, then we will not carry forward this previous cell state into the next state. If it is 1, then so what happens here is essentially a bitwise multiplication. What is bitwise multiplication is, if it has a matrix of the 10 values, we'll multiply 0 into all the 10 values. If it what that is what bitwise multiplication is. So this is bitwise addition, this is bitwise multiplication, or they would call it as point-wise addition, point-wise multiplication, which is essentially the same. This forget gate output decides whether the previous cell state should be carry forward or not, and then we have already calculated the new cell state, candidate state, correct? We will also use that to compute the new cell state. What is the state of this particular cell? This is where the information about the iteration is stored. Remember, we said that it stores each state information in a content addressable memory system, correct? That information will be held in the C of T, which is coming here. If you look at the animation clearly, it is coming here. So the next thing that we need to do is, we'll try to decide on what is the output that we are trying to do. So for this particular input X of T, we will generate an output. Whether that outputs hidden state and the candidate state, whether that outputs hidden state information has any weightage, that is calculated in the hidden state here, and then that particular outputs candidate state or the new cell state information will be carried forward. So this operation is going to be repeating. So when we started previously, we had a hidden state, we had a candidate state, which is T minus 1 and T minus 1, H of T minus 1 and C of T minus 1, correct? So these two has to be moved on from cell to cell, yes? So that is what we are calculating here. C of T minus 1 and H of T minus 1 is what going to be the output of the next cell. These two are going to be the input for the next cells, where X of T plus 1, here we have seen X of T, just X of T, which is our input vector. The next cell will have X of T plus 1, and then C of T minus 1, and then H of T minus 1, which is calculated per this input, which is X of T. Okay, I hope it's clear, and I hope the values or the mathematical intuition behind the LSTM is clear for everyone. Okay. So now, what is different in GRU? As I said earlier, GRU is the one which got rid of the memory requirement as well as the computational complexity problem of the RNN architecture. How did they do it? It's very simple. They got rid of the cell state information. Okay, they just said that if I have a hidden state to transfer, I will check whether this particular input needs the hidden state or not. If it doesn't need this information, I will just hold the information of the hidden state alone. I will never use the hidden. I will never have the cell state information of particular input. So if you see here, what is the final output here? The candidate state or the new cell state from here will be stored across each and every cell, correct? But what is happening here is, we are only storing the hidden state across each and every cell. We got rid of the candidate state. That solves the memory requirement problem. And here we had 3 sigmoid function, 2 tanh function. Here we have only 2 sigmoid function and 1 tanh function. That necessarily got rid of the computational complexity. Okay. So in GRU, the difference is, instead of having so many gates and instead of having so many vectors, we got rid of all those and we said I need only 2 gates. One is going to be a reset gate and one is going to be an update gate. So what happens in reset gate is, if the particular input doesn't require the previous state information, I will reset that previous state information for this particular input alone to 0. Okay. If that particular input has this, needs this information, then I will update that information to this particular input and then I will calculate it. That is what is essentially happening here in the GRU, right? Now GRU versus LSTM. uh, GRU, one of the main problem with the GRU is it's not explored very well. So they said GRU has very less memory computation, GRU has very less complexity, memory requirements as well as computation complexity. But since it started so late, that is 2014, people hasn't started using GRUs widely. Just take a look, go into internet and search like RNN architectures. You will receive a bunch of medium or a bunch of analytics vidya or any kind of blog articles only regarding to LSTM. GRU has never accepted as an RNN architecture widely across all developers or all tech people, because one unavoidable reason is GRU came into picture in 2014. In 2016, they started using transformers, which is another concept, which is most similar like an RNN architecture, but it uses an attention mechanism. Then the evaluation of RNN stopped, and the transformers time began. And so comparing to LSTM, GRU has very few parameters. It has only 2 weights, which is update gate weight and reset gate weight. Also, it works faster and it needs very less number of data, since it has very less number of gates and it has very less number of state information. It needs very less number of data. There is a committee called empirical evaluation, which uses there is a committee called empirical evaluation, which goes across different architectures, different ideologies, different topics that has been coined in the computer terms, and then they will say the pros and cons of that particular topic or architecture. So according to the empirical evaluations, gated recurrent neural networks versus LSTM, there is no clear winner, because LSTM performs very well on a huge chunk of data. Okay, but when it comes to time complexity and memory restrictions of the LSTM, it is huge. So there is a trade-off, right? Everywhere we go, there will be a trade-off, like which to choose, where to give importance, what should I take care of more instead of what I want right now. So that trade-off is also here. Even in machine learning terms, there is a trade-off between precision and recall. If you train a model, you most probably expect the recall to be high, because every discriminative model's recall will be high. But if you want precision, then you need to train a generative model, which will again reduce the recall of that particular model. So there is essentially a trade-off happens between precision and recall. Like those, there is an essential trade-off that is happening between memory requirements, computational complexity versus the performance. And people haven't tested GRU's performance across different data points or across different informations. That has not been done till now. So we have to wait for it. As I said, before getting into those, uh, the the evolution of transformers just stopped, and RNN started, and RNN just died down or dialed down towards its lower tone, and it's not been widely used. By RNN, I mean no, not widely used. I mean RNN is not being uh, re-evolving since the development of transformers. But as I said very first, knowing the history is important. Transformers started with the intuition of an RNN, with the idea behind the RNN. So if you don't know RNN, you will never be able to catch up with what is happening in the industry, where it is going on, how the research are taking place, what are all the research types that are happening. You will never be able to catch up on that. Okay, GRUs, both the GRU as well as LSTM's architecture yield a comparable performance based on the hyperparameter tuning. So the ideal situation is you should be able to come up with the right architecture that is suitable for your problem. That is the ideal situation. So the next topic is long-lived transformers. It says uh, which is nothing but from LSTM, long-lived LSTMs, which is nothing but from LSTMs. There are so many things that are evolved. One is attention mechanism. Sorry, attention mechanism. Attention mechanism is mostly what it involves is, let's say you have a chunk of data and you want your model to train on the chunk of data based on this particular information. But since the data is so huge, since the data is so huge, you can't expect the model to perform really well on this particular data. So what we will try to do is we'll try to provide attention across a particular zone so that the model will learn the necessary information that we want the model to learn. So that is what the attention mechanism is. And then came in the BERT. It is developed by Google. BERT is bidirectional encoder transformer model. That is where the encoder architecture started. That is where the transformers actually started. So BERT is nothing but we have a huge set of language information trained on this particular model. So the model has been already trained on. All you have to do is import that model and do your task, whether it is text classification, whether it is sentiment analysis, whether it is anything to do with semantic similarity or anything to do with information retrieval, indexing, anything. You can do it on the BERT model. As we all know, recently this new model came into picture, which is GPT-3 by OpenAI. OpenAI is one of the open source initiative from Elon Musk, the founder of Tesla, PayPal, that guy. So those guys created a model which is trained on billions of parameters. In our term, billions is 100 crores. We train a neural network model just on some 15, 16 parameters, and we'll get confused why the model is performing like this, what is the expected outcome, and what is the happening outcome will get we are getting confused. But those guys have trained a model that has billions of parameters, and they have open sourced it. You can use that model. It is the very first time that a model is performing a generalized task. What I mean by generalized task is, if you train a model to predict the house price, it will only predict the house price. If you train a model to classify a tweet sentiment, it will only classify the tweet sentiment. But this GPT-3 model is able to generalize across different things. If you give it a text classification data, it will do the classification. It will, if you give it to a sentiment if you give a sentiment analysis data to it, it will do the sentiment analysis for it. If you give a text summarization problem, that is, if you give a paragraph and you expect a brief sentence that represents the paragraph out of it, it will give you a text summarization. Okay, so if you have time in your free time, leisure time, try to go and search about this open AI gym models. They started this GPT-3.1, and from there it has been evolved to GPT-3. They started with GPT-1, now it's GPT-3. The 3 is supposed to do wonders, and it's actually rocking the AI world right now. People are widely accepting that GPT-3 is going to change everything. They also say that it's going to constitute for Terminator and those Skynet kind of things, because it's actually able to understand and generalize across different actions or different times or different informations, different contextual informations. Okay, so one guy has created this website where he uses OpenGPT-3, where you can talk to the model using anything. Like, you can say something like, if you want to start a conversation about one particular movie, you can say, this particular movie I want to start a conversation with, and then it will talk for hours and hours about this one particular movie. Even we can't talk like that. It will be able to talk. It will have all those informations attached, associated to it. So then came in zero-shot learning. Zero-shot learning came in with the Siamese networks, which is an interesting concept. If you have time, take a look at it. Siamese networks are an interesting concept. It involves science intuition behind it, which is the concept of Siamese twins. The Siamese twins are people who has single body but two different heads. I know I basically think that most of the people are Tamil here, so you would have seen the movie Matran, right? Where most likely like Matran, where they have a single body instead of two bodies. Like, consider there is a single body and two heads. There are two different brains in it. There are two different head functionalities in it, but the heart is single. They have only a single heart or a primal heart. So that is what the Siamese twins are. From that, they created this network called Siamese network. So that is why initially I said that have the right intuition, know the history, see how people are developing. They developed a new form of neural network called the Siamese neural network, and that neural network is an inspiration from the human body, which is called the Siamese human form, which is called Siamese twins. So zero-shot learning is nothing but, instead of training through thousands and thousands of data points, you just have to train through some few data points from which the model will be able to understand one particular task, and it will do the task very well. Okay, and then transformers came in, and then sentence transformers came in. Transformers are nothing but attention-based encoder architecture, which is also similar to BERT, but their architecture is slightly different. Take a look at it if you have time. So transformers, initially it started like it will provide embeddings for each and every word, and then the sentence transformer came in. which will actually provide an embedding for each and every sentence. So why LSTM, why the attention mechanism or the BERT or the transformers evolved is, the problem is out of the word vocabulary, out of the word domain. What is the meaning of out of the word vocabulary is, if you have a text data which represents a news article and you are trying to and you trained a model on it, and let's say a new tweet comes in instead of news data, if you pass the tweet to this model, it will never predict properly. That is out of the vocabulary. The vocabulary used in news is different from tweets. Newses are vernacular, where tweets are colloquial. Correct? In tweets, what we do, in tweets or WhatsApp messages, what we do is necessarily sending in the format that we understand mostly. Correct? But here in the news article, it's supposed to be structured, it's supposed to be well articulated. So the vocabulary of these two will be different. So if you train a model on this particular vocabulary, the words that it has seen on this particular news article data will not be available in the tweet data. So since there is new words coming in, it will try to undermine those words and it will try to highlight the words that it has already seen from the news data and try to give a prediction, which will actually fail in your case. So that is the one problem out of the word vocabulary. So these BERT, zero shot learning or sentence transformers has a huge corpus that involves all the words in an English vocabulary. And then the other problem is out of the domain. So that's again the same example. Let's say you have collected a news article from all the news article about Donald Trump, and you are trying to collect tweets or same news article, but you are collecting news articles for the Chernobyl incident or for the stock market crash. Okay, so news article about Donald Trump is a different domain, which is slightly into political and slightly into business. News article from Chernobyl incident is more into tragedy, is more into accidents and those zone. But here it is in the zone of business as well as political. So these two are different domains, and the vocabulary used in these two will be different. So the model will not be able to understand from the training of one domain into the testing on another domain. That is another problem. And this problem is also solved by the transformers or the BERT or the sentence transformers. I'm basically, I work on LSTMs, I work on GRUs, I work on RNNs, and no, I'm not the authority of all those things, but I have slight knowledge on it in a level to say that I have published a paper recently on using deep learning, which is LSTM. It's essentially an LSTM model which which uses polarity. That is, by polarity I mean the sentiment of a particular tweet, whether it is positive or negative, sentiment of a particular news, and the historical data of any stock price, and we try to develop a model that will use these three features to predict the volume movement in the stocks that are traded at any given time. This has been accepted and published in the ACM conference. So the conference is on International Conference on Big Data Services and Intelligent Computation. It's an ACM conference conducted in China. So I published a paper on it, waiting for it to get it into a journal. So any questions so far? Any doubts? Feel free to ask anything. That's it. So thank you so much for listening. You have been a wonderful crowd. I hope I'm able to convey information in a manner that you can possibly pursue or pursue on your own venture. So, any questions, any doubts, please feel free to ask.
Sir, can you please explain the concept of LoRaWAN technology for deep learning?
Sorry, come again. Concept of?
LoRaWAN, LoRaWAN technologies.
Uh, okay, I'm not able to hear clearly. Can you type it in the message, the chat box?
Yes, sir. Yes.
Can you give? So, you're asking about a network protocol, is it?
Yes, sir. Yes, sir.
Okay. You are going to use this in some kind of project, correct?
Yes, sir.
Okay, got it. So I am a kind of person who also involves in cyber security and those kind of stuff. So I know a little about wide area networks, and so if the question is more generalized, can you ask anything particularly? So about LoRaWAN, what do you want to know?
Sir, this kind of protocol with respect to this LSTM or GRU networks combined together for cyber security attacks like that.
Oh, okay. Okay, so got it. Okay, so the question is whether how to use, not whether, how to use cyber security, the protocols, network related protocols, how to include those protocols into these kind of information, these kind of neural networks and those stuff. That's the question.
Exactly.
Uh, Okay, cool. So to answer this, actually, this is a very nice ideology because it involves time step, right? Any cybersecurity attacks involves time step. So based on the data gathered, since it's a wide area network, there is going to be an cloud-based internet storage, which uses which is used to store all the network related information in one particular place. Or if the LoRa protocol is used in an Internet of Things, or the if it is used in any IoT related problems, then there will also be a cloud, or there will also be a data storage facility, right? So one thing that we can do is we'll try to track this information. We'll try to log this information anytime. If but what are all the parameters that is available from that wide area network, will store that information into one place at each time step. Then we'll try to so how to use that information in this LSTM is, you have a data point that is changing across time, correct? Then what you can do is associate that as an LSTM data point and try to generate a LSTM model, which will actually be able to predict any attack, or given the particular state information, it will try to predict whether an attack is possible or not. This is essentially a classification problem where we use the time step, or where we use the time related information into it, and then try to predict it accurately, which is possible. Uh, but I don't know whether it has been already done or not. I'm not sure about that.
Okay, sir. Thank you. Thank you.
Yeah. Also, there is another question which is related to dataset link for brain tumor. Okay. So there is this site called one second. Uh, there is this site called Data Worlds. I'm sending it to you on chat box. Just give me a sec. I'm just searching for the domain. Okay, it's data.world. It's an open dataset forum where you will be able to find all kinds of data in it. Okay, it's data.world. Anyone who has any need for data, any need for any kind of data, go and search in that data.world data.world website. You will be able to find it, or else you can go for this. So if you need any kind of web related data, you can go for common crawl. I'm sending that too in the chat box. Please refer to it. There is a website called Common Crawl, and there is a website called Data World. Okay, I'm typing it in. WORLD. Okay. There is a site called Common Crawl. There is a site called Data World. These two sites hold all the information, that is needed, all the data that is available. So Common Crawl is something like whatever information, any kind of tweets, news, job related information, any domain based data which is available in the internet, this Common Crawl will have it. Okay, it has 300 petabytes of data. 300 petabytes. There is a MB, and then there is GB, which is gigabyte, and then there is TB, which is terabyte, and then there is petabyte. Common Crawl has 300 petabytes of data. I'm sure whatever kind of information, whether it's about lung cancer, whether it's about modality image, or whether it's about brain tumor, whatever kind of data you need, whether it's about sentiment analysis, anything, whatever the kind of data you need, you will find it in either in Common Crawl or you will find it in Data Worlds. Also, there is another a site called Kaggle, which is a data science or machine, what do you call that, AI platform, which hosts hackathons and those kind of stuff, which will also have a open dataset format where you will be able to find all these datasets that you are trying to access. Just search like lung cancer Kaggle dataset. You will find immediately a link. Lung cancer data world, lung cancer common crawl. You will definitely find a link, I'm sure. Any other questions?
Thank you, Maya Bharati. Hope there is no doubts from the participants. So we will meet after this lunch at 2 p.m.
Any other link for image? Okay, for image, there is COCO, which is a collective initiative collected by Microsoft. You will have COCO. Just search for COCO image dataset. I'm sending you the search term. Use that to find, or wait, I'll get those for you. 1 second. Yeah. So this is the, I mean, the name is Kokilavani, right? Kokilavani, I have posted a link in the chat box for image dataset. If that dataset doesn't have your images, doesn't have the kind of images you need, you can also search for Google datasets. So there is a concept called there is an initiative by Google where instead of, so everyone has been oh, okay, but the extension is a major problem. What do you mean by extension? I don't understand it clearly. Extension meaning the file format, is it? So another thing that I was saying is there is this file type. Okay, so what is the problem with the file type? Coco dataset has, oh, it it has images, right? What is the file type you're seeing? Are you receiving any numpy files, that is .npy files or something like that?
You can unmute and speak.
Yeah, you can also unmute and speak. I'm sorry.
Yeah.
Yeah, as I was saying, there is also this data search research.google.com, which is a site that provides any kind of data set that you search for, any kind, not only image, any kind. So it's like you're using Google to search something, right? Like that, the same terminology you can use, but the results will be, instead of articles, news, or something like that, this will only be data sets. Oh, okay, there is a mic problem. No issues. You can send it in the chat itself. I'll be happy to answer. What is the problem with the file type? Can you mention the file extension in the chat box? I'll try to see. Or you can also state the purpose of the image data or the kind of image data that you're looking for. Both the things. If the file type is the problem, then let me know the extension. I'll see what I can do. Or if there is a problem with you can't find the right data for your particular image problem, let me know what the problem is. I'll try to come up with something in the afternoon session.
Any more doubts from the participants? I hope there is no doubt from the participants. We will close this forenoon session. Again, we will meet by 2 p.m. Thank you, Mia Pardi.
Okay. Thanks, everyone. Thank you. Bye-bye.